Well, we will follow the lecture notes by Fatih Hoca. I will skip some of the content, so this is for electrical engineering guys. But we will follow the important aspects for computer engineering students. So, well, what's the signal? We will first start with the definition. Actually, a signal is the variation of a physical or non-physical quantity with respect to one or more independent variables. Well, signals typically carry information that is somehow relevant for some purposes. So this is the very formal definition of a signal. Well, here you see, as an example, a capacitive and inductive circuit, RLC circuit. You have the input at the left-hand side, there is the current, and in the right-hand side you have your output signal. Or as another example, acoustic signals, actually some speech voice signals, in other words. They are simply, they are formed as the acoustic pressure as a function of time, so the acoustic pressure changes in time, so you have acoustic signal. Speech, for instance, is produced by creating some fluctuations in acoustic pressure. So when you speak, the acoustic pressure in the microphone is changing, and this change is sensed by the microphone and converted to some electrical signal. So you speak, there is a microphone, and the microphone converts the change in the acoustic pressure to some electrical signals. Or picture, well, I'm sure you know what a picture is. Actually, if you take well, actually, I cannot continue with landscape mode, unfortunately, because I will take notes on the PDF. So please arrange your screen or resolution so that you can see all of the content. Well, a picture, if you go and take the Ceng 441 lecture next year, you will have a more practice on pictures and images, image processing. Actually, a picture is nothing but it's a brightness change, it's a brightness function, and the brightness changes with respect to two special variables, x and y, in 2 dimensions. And you have, if you have a camera and if there is a scene, there is a light, if your camera senses the photon energy, then photon energy is converted to some electrical signals, and the electrical signals is digitized, and it is your digital image at the output. Well, you can have many other examples, such as sequences of bases in a gene, or sequences of daily stock prices in financial market, and so on. Well, we will mostly refer to the independent variable as time. So the independent variable may not be time, it may be location or any other independent variable that you can think of. But for our signal processing purposes, we will think that the independent variable is time, and it's denoted by t. Well, also we have 2 types of signals. We may have continuous time signals or discrete time signals. In continuous time signals, the independent variable is continuous. So what I mean is this. Assume that I have such a signal, let's say t, and this is my f of t. Well, in this f of t, if this is a continuous time signal, and a continuous independent variable t. So when you compare it with the discrete case, so in discrete case, this is my discrete signal, and in this discrete case, the independent variable takes some discrete values. So in continuous, I can have any value here, let's say 1.5. But in discrete case, I must have some discrete time indices. So this slide, this representation is very clear. Well, in discrete case, your independent variable is discrete, it's not continuous. it can have discrete values. But in continuous case, the independent variable is, as the name implies, continuous, and it can have any intermediate value depending on the signal. Well, as a note, discrete time signals are undefined at values other than specified discrete values. So in this example, your signal is not defined here. So this is, let's say, 1.5. At 1.5, your signal is not defined. So they are defined only for discrete values. Well, speech is a 1D signal, as you know. So you speak, the microphone converts your speech to some signals, and it is in a 1D form. Images, on the other hand, is a two-dimensional function. So I have my image that I share through Instagram. I post to Facebook, so it is a two-dimensional signal. Well, what about video? It is a three-dimensional signal. Of course, you have a series of images, so the images are shown one after the other. So video is a 3D signal. Well, in this course, the signal, continuous time signals is really represented by x of t, and t is a continuous signal. Okay. On the other hand, discrete time signals will be represented by x of n, and in that case, n is discrete. Okay. So this is how we will be representing discrete time and continuous time signals. Well, most physical signals are in continuous time, but of course not all. And in general, a discrete time signal may be obtained from the phenomena that is inherently discrete. For instance, I have my students attending the lecture, and in that case, I have discrete number of students. So if I, let's say, count your age, where you were born, now I have a discrete signal since I have discrete students. Or you can obtain discrete time signal by taking samples from a continuous time signal, just like the blood pressure. So your blood pressure is changing in a continuous way, but you are just taking some samples from the blood pressure at specified time instance. Well, on the other hand, as our second definition, system is defined as any process in which input signals are transformed to output signals. So you have some inputs and you have some output signals. So this is how we define a signal, a system, sorry. Well, you see here an example in previous slides. You have voltage at the inputs and you have voltage at the outputs. We will discuss the systems in more details in the upcoming section. The transformations of independent variable of signals is an important idea. So you can shift or you can scale or apply the combination, or you can have some hybrid transformations on the independent variable of signals. The first example is a time shift. So I have the signal x of t, and I construct y of t by simply shifting the independent variable. So how does it look like? Let's say I have this x of t, and let's say it is just such a signal. Okay, and let's assume that this is my peak value. Then let's shift this signal. If I shift this by t0 amount, well, in the original, the signal was starting from 0, but now the shifted signal is starting from t0. So this is my y of t. and it is nothing but x of t minus t0. So it is shifted t0 sample. In this example, if t0 is positive, the signal will be shifted to the right, and if it's negative, otherwise it will be shifted to the left. We will see more and more examples. What about a discrete time signal? Let's assume that I have such a discrete time signal. Let's say it is like this. Okay, so this is my 0, this is x of n, this is n. When I shift my signal, well, unfortunately, they have gone. Okay, let's draw once more. This is my t0. This is x of t minus t0. If I have a discrete signal, let's say x of n, and it is like this. If I shift the signal and obtain x of n minus n0, let's say n0 is a large number, not to confuse those two graphs. Okay, this is my shifted signal, x of n minus n0. So the original signal, the first peak was at 0, but now it is here. The first peak is at n0. So this is my shifted signal, again, to the right or to the left, depending on my n0 value. Well, in general, what do we have is this. If we have x of t, and it is a signal in between, let's say, t1 and t0, the shifted signal, x of t minus t0 is, this is t2. If the peak is in between t1 and t2, the shifted signal, x of t minus t0, is in between t1 minus t0 and t2 minus t0. So this is t. So this is a general way, and depending on t0, the signal may be shifted left or to the right, and we will see more and more examples. So what about time reversal? Well, time reversal is actually reflection around the origin. So if you have such a time shift, time reversal, y of t is x of minus t. So let's say I have such a signal. Let's say this is t1, this is t2, okay, and it is 0. This is the origin. So this is my x of t. In this case, if I do time reversal, I simply reflect my signal around the origin. So here this is minus t1, this is minus t2, this is my, again, origin, x of minus t, this equal to y of t. So the signal will be just like this. Okay, it is just reflected around the origin, and this reflection gives me y of t, which is simply x of minus t. And the idea is actually, well, they are going. I'm not sure why they are going, but let's draw once more. So this is t1, this is t2, plus t1 plus t2. If you reflect again, this is what you will have. Okay, this is my minus t1, this is my minus t2. x of minus t. Okay. So the idea is similar for the discrete case. Well, the second idea in the slide is time scaling. In time scaling, you have this x of t, and this x of t is converted to the y of t, which is x of at. And in discrete case, we have similar. We have x of n, and y of n is simply x of bn. Here, please note that b is an integer. Well, in discrete case, these discrete signals are defined for integer values, discrete values. So here, I again have b as an integer. So what are my examples? Let's say I have here t, x of t, and this is my t0. Well, what about if I plot y of t? Which is x of at, this is what I have. T0 over a now is the limit of my signal. In this case, x of t is maximum at t0, but now y of t is maximum at t0 over a. Well, what about discrete case? Let's plot a discrete example. Let's say I have x of n. This is my n. So this is 0, 1, 2, and 3. What about, let's say, y of n is equal to x of 2n. So what do you say? Y0 is x0. So put here 0, okay? Y0 is x0. Y1, put here now 1. Y1 is x of 2. Y2 is x of 4, and it goes on like this. So what is this? This is my yn. Okay, I will take only the high samples. So this is 1, 2, and 3. Let's say it goes on like this. So this is my yn signal. Well, in general, what do we have? If a is in between 1 and infinity, we have compression. Well, the signals are compressed. If we have a in between 0 and 1, we have expansion. So the signal is expanding. If we have -1 and 0 is a in between -1 and 0, we have reflection. Reflection plus expansion. And if a is in between -infinity and -1, then we have reflection plus compression. So depending on the sign of a, we have reflection or not. Depending on its value as compared to its, let's say, absolute value compared to 1, it is either compression or expansion. Actually, I will have example for all of those cases. Well, here we have a note. X of at is always defined for a is an integer, is a real number. So in x of at, since I have a discrete, since I have a continuous signal, my scaling factor a can be a real number. So it must be a real number. Well, on the other hand, for discrete time signals, so I have y of n equals x of bn. My b must be an integer. Okay, so b is an integer in discrete case. So this is for xn. So these square brackets are showing me that I have a discrete signal. So x, in that case, x of 2n is valid. So this is a valid transformation. I have square root of 2n. So square root of 2 is not an integer. So this is an invalid scaling. What about n over 2? I have n over 2, so 0.5 times n. So this is again not n, not a valid scaling, time scaling. So here I have an example. Let's again assume that I have such an x of t, sorry. I will plot a continuous time signal. This is 1, this is 1, this is 2. Okay. This is my x of t. Now I will try to find y of t, which is x of minus t plus 1. So first I will find x of t plus 1. Let's plot x of t minus t plus 1. So it will start from minus 1, just like this. Okay. So let me erase this. They are too near. Okay. So let's plot once more. This is my x of t plus 1 from minus 1 up to plus 1. So what do you say? I have x of t, which is in between 0 and 2. It is constant from in between 0 and 1. Then it's decreasing from 1 to 2. T is from 1 to 2. So what about x of t plus 1? What do you say? So since I have a positive shift factor, so I have x of t plus 1, so I will say that the signal will be shifted to the left. So this is it. So it will be in this area. Okay. So it is simply this. Okay, this is 1. So my x of t plus 1 is nothing but x of t, but shifted to the left by 1 unit. So what about x of minus t plus 1? X of minus t plus 1. So remember time reversal. Now I will reverse the time of x of t plus 1. So it will be nothing but, here I have minus 1, here I have plus 1. So it will be just the reflected signal. Okay, this is 1. That's it. So the signal will be first shifted. So I obtain x of t plus 1. Then in order to obtain x of minus t plus 1, I take the time reversal. Well, the easiest way to check whether your output final signal here is true or not is this. Check the values. So put here 0. So what is y0? Y0 is simply equal to x of 1, right? Put here 0. Minus 0 is 0, plus 1 is 1. So y0 must be equal to x of 1. So what is y0? If you check, this is y of t, remember? This is y of t. So y0 is simply here 1. So both are equal to 1. So first value is 0. First value is true. Or another, let's say, check, let's say y1. What is y1? Y1 is nothing but put here 1, put t equals 1, it is x of 0. And both are equal to 1, that's true. Let's check y of minus 1. What is y of minus 1? It is 0. And put minus 1 here. Put minus 1 here. So what is it? Y minus 1 is equal to x of 2. It's equal to x of 2. And it is 0 in this case. So by just checking a number of values. You can check here again, let's say minus 0.5 or 0.5, and check whether your result is true or not. Now I have a discrete example. Find and plot y of n for x is for find y of n, which is equal to x of minus 2n plus 1 for x of n, let's say n for 0 smaller than or equal to n smaller than or equal to 5. Okay, so first I will plot x of n. What's x of n? So this is my x of n. This is 0, 1, 2, 3, 4, 5. So it has 6 values, 0, 1, 2, 3, 4, 5. So it is 0 at 0, it is 1 at 1, 2, 3, 4, and simply 5. Okay, this is 1, 2, 3, 4, 5. So this is my x of n. So I will find x of minus 2n plus 1. As in the previous case, I will first start with shifting. So I will find x of n plus 1. What is x of n plus 1? Actually, since I have a positive shift, the signal will be shifted to the left. Let's plot this. X of n plus 1. So it will start from minus 1, 0, 1, 2, 3, and 4. It is 0 at minus 1. It is 1 at 0, 2, 3, 4, and 5. Okay, so how can you check whether this is x of n plus 1 or not? Simply put here, let's say 1. So if I put here 1, what do I have? X of 2. So what is x of 2? It's simply 2, and it is equal to this value. Okay, so you can check whether other values are true or not. Then what do I have? I have a time reversal. Okay, I have a time reversal. Then I will do time reversing operation. So let's raise this one. Time reversal operation. Okay. This is my time reversal operation. Let's say this is 0. I'll somehow go over here. Minus 4, minus 3, minus 2, minus 1, and 0, and this is 1. This is my n. This is x of minus n plus 1. So I will simply reverse the time. So at 4, it was 5, but now at minus 4, it is 5. At 3, it was 4, but now at minus 3, it is 4. 3. This is 2. Now I have 1 here, and I have 0 here. So this is somehow confused, but I do nothing but time reversal. At 4, it was previously 5, but now it is 5 at minus 4. It was 4 at 3, now it is 4 at minus 3. So this is my x of n plus 1. Okay, a single step left. What is this? Now I will find x of let's do this. I will find x of minus 2n plus 1. So if you remember the previous case, let's plot once more. Minus 4, minus 3, minus 2, minus 1, 0, and 1. So it was this. This is 5. This is 4. This is 3. This is 2, this is 1, and this is 0. 4, 3, 2, 1. So now I will find x of 2 n plus 1. So this is my, remember, x of minus n plus 1. Now I will do time scaling. So I will get only the odd samples, only the even samples, sorry. So x4 means, so the value here at minus 4 here now will be at minus 2. So it will be 5 at minus 2. I will skip minus 3 and take minus 2 value. So the value which is 3 at minus 2 here now will be at minus 1. This is 3. At 0, I will have 1 here. So previously, again, it was 1 at 0. So scaling does not change the 0 value. So this is my n. This equals to y of n. Okay. That's it. So when you compare the left-hand side and the right-hand side, x of minus 2n plus 1 simply gives you the even samples, and this is my yn, that is minus 5 at minus 2, it is 3 at minus 1, and it is 1 at 0. I can simply check whether this is true or not. So let's check y minus 2. What is it? This must be equal to x of 5. Put here minus 2. So minus 2 times minus 3 is plus 4, plus 1 is 5. So y minus 2 must be equal to x of 5. Y minus 2 is equal to 5, and x of 5 is 5. So this is true. So I will check, let's say, y minus 1. What is y minus 1? Put here minus 1. Minus 1 times minus 2 is plus 2, plus 1 is 3. So this is supposed to be x of 3. So y minus 1 is 3, just like here, x of 3. So this is true. Let's check y0. What is y0? y0 is 1. And if I put here 0, it must be x of 1. And so what is x of 1? It is 1. So this is again true. What about y1? y1 must be equal to, put here 1 now, minus 2 plus 1, it makes minus 1. And what is x of minus 1? It is 0. And y1 here is again 0. So this is true. So this is a simply double check of the formulation. And you can verify that what you do is true with this simple check. Well, the next idea is periodic signals. So let me erase this part. So the next idea is periodic signals. A signal, a periodic continuous time signal x of t has the property that there is a period capital T, and it is a real and a positive number. X of t is simply x of t plus capital T for all t values. So it means that with period t, the signal repeats itself. Okay, the value at x of t is simply equal to the value at x of t plus capital T for all t values. And in that case, it is said that x of t is periodic with capital T. Well, you can also define periodicity for discrete time signals. They have the similar idea. X of n is equal to x of n plus capital N, again for all n. So this means for all n, so for all possible n values. But here now we have an additional constraint. N must be equal, n must be a positive integer. So it must be an element of Z positive, okay? It must be an integer other than 0, positive integer other than 0. It cannot be 0. So here, capital T again cannot be 0 because you see real positive. Similarly, capital N is either 1, 2, 3, or 4, 5. So it goes on like this. It is positive and it is integer. It is non-zero. Well, I have some examples in this case. Well, let's plot a periodic x of t. Also, it continues in the negative side. So this is capital T. These are capital T, by the way. This is my x of t. And please note that x of t is actually a periodic signal. The value at 0 is equal to the value at t. It's equal to the value at 2t. Or the value here is equal to the value here. And the difference is simply t. Okay? This is my periodic signal. Discrete, a continuous time periodic signal. Well, what about a discrete example? Let's plot a discrete example. High sample, let's say low sample, and high sample. Again, high sample, low sample, high sample, high, low, high. So I have such a, let's say, x of n. Let's say this is minus n, this is 0, this is capital N. You see the value at minus capital N is equal to the value at 0, it's equal to the value at n. The value at, let's say, minus n plus 1 is equal to the value at 1, and it's equal to the value at n plus 1. So this difference between all of those samples is capital N. So the signal repeats itself with the period capital N being an element of positive integers. Well, here we have again a note. If x of t is periodic with capital T, then it is also periodic with 2t, 3t, 4t, and all integer multiples of t. Okay, so the signal repeats itself here, let's say, in this case, repeats itself with t, but also repeats itself with 2t. This signal is equal to this signal, right? So this is the general idea. The same also holds for discrete time signals. The signal repeats itself with n, capital N, but also with capital 2n. Okay? But here, the fundamental period, it's important, the fundamental period is the smallest positive t for which x of t is periodic. So I can here say that my signal is periodic with t, my signal is periodic with 2t, it is periodic with 3t, but the smallest of those ones is capital T, and this is my fundamental period. Okay, this is important. It must be the smallest of all of those, and of course it must be positive. Okay. Well, the next idea is even and odd signals. The definitions are quite easy. A continuous time signal is even if it satisfies this property. So x of t is equal to x of minus t. It is odd if x of t is equal to minus x of minus t. So let's see an example. So let me write this. I cannot erase it. So let's draw it once more. So this is my origin. This is my t. This is 1. This is -1. This is 2. This is -2. But it's hard to draw on the tablet. So assume that this is symmetric around the origin, around the vertical y-axis. So you can see that the value here is equal to the value here. The value here is equal to the value here. So this is simply symmetric around the vertical y-axis. So this is my x of t, which is an even signal. What about an odd signal? Let's draw an odd signal. This is -1, this is +1. Okay. So x of -1, let's say here, this is, let's say 2. This is -2. So x of -1 is 2, but x of +1 is -2. So this relation holds, you see. Or x of -2 is 0, so it doesn't change. If x of -2 is equal to x of 2, they are both 0. But let's say here I have -1.5. X of -1.5 is 1, but x of +1.5 is -1. So this relation holds for this x of t. So it is an odd signal. Okay. The same idea actually holds for discrete time signals. Here you see the same formulation. For all n, x of -n is equal to x of n. If it is even, x of n is equal to minus x of -n if it is odd. I will have just a moment, then I will finish. Please note that any signal x of t can be written uniquely as a sum of its even and odd parts. So if I have, let's say, x of t, let's say, I can write this as x even of t plus x odd of t. Okay, this is the even part, this is the odd part. But how can I find xe and x odd of t? So it is simple. The even part of x of t is nothing but x of t plus x of minus t 2. Or the odd part, on the other hand, is simply x of t minus x of minus t over 2. You can check by yourself that this signal is odd, this signal is even. It is your exercise. So also as an exercise, let's say I have x of n, which is 1 for n subordinate equal to 0 and 0 else. Find x odd of n and x even of n. Okay, if x of n is 1 for n larger than or equal to 0, or and 0 else. So what is x of n, by the way? 0, 1, 2. It is this, right? All samples are 1. It goes on like this, and it is 0 otherwise. This is -1, this is -2. So please find odd and even parts of the signal as your homework or exercise, let's say. So next time we will continue with discrete time unit impulse and unit step sequences. So these are again important sequences. So next time we will continue with that. So let me stop recording.